The calculation that we are doing today is from the topic of refrigeration and heat pumps in thermodynamics. Let's look at the question. In the question it says there's an ammonia vapor compression plant, and the compressor power input is given as 7,000 watts, or 7 kilowatts. The mechanical efficiency is given as 90%. The ammonia is dry saturated at -6 degrees Celsius at inlet to the compressor. After the compression, the pressure is 11.67 bar. The isentropic efficiency of the compression is 90%. You need to calculate the mass flow rate, the coefficient of performance of the refrigerator, and coefficient of performance of the heat. From the diagram we have the refrigeration cycle or the heat pump cycle. We assume that the first point is the point before compression, second point is the point after compression, third point is the point after condensation, and fourth point is after the expansion in the throttle valve. Please note, from point 1 to point 2, it's isentropic compression. From point 2 to point 3, it's constant pressure heat rejection. From point 3 to point 4, it's isentropic expansion, and from point 4 to point 1, it's constant pressure heat addition. Let's start solving the calculation. Our aim is to calculate the enthalpy values at each point in the cycle. So for the first step, we look at the ammonia table in the steam table, and for ammonia at -6 degrees Celsius, the H1 is equal to Hg from the table, that is 1,437.6 kilojoules per kilogram. As we know in the condenser, it's a constant pressure heat rejection. That means the pressure before the condenser and after the condenser is the same. So P2 is equal to P3, that is 11.67 bar as given in the question. Again, from the ammonia table, when pressure is 11.67 bar, we will get H3 is equal to HF, and that is 323.1 kilojoules per kilogram. Now from the ammonia table again, we can find the entropy at temperature -6 degrees Celsius. So when T1 is equal to -6 degrees Celsius, you can see that the entropy value S1 is equal to Sg from the table, and that is equal to 5.419 kilojoules per kilogram Kelvin. And since the compression is isentropic, the entropy remains a constant. So S1 is equal to S2, that is equal to 5.419 kilojoules per kilogram Kelvin. We know that in the question it says the isentropic compression efficiency is 90%. For the sake of the calculation, let's assume that the efficiency is 100%. For an ideal scenario from the ammonia table at pressure 11.67 bar for 100% efficient compression, entropy S2 is equal to 5.417 kilojoules per kilogram Kelvin, and ideal H2 is equal to 1610.5 kilojoules per kilogram. So from this we can see that the ideal change in enthalpy after compression is ideal H2 minus H1, and that is 172.9 kilojoules per kilogram. But from the question we know that the isentropic compression is not 100% efficient, and the efficiency is at 90%. So we can find the actual change in enthalpy of the compressor. The actual change is the ideal change divided by the efficiency, that is 172.9 per 0.9, which is 192.111 kilojoules per kilogram. So finally, H2 is equal to H1 plus the actual change, and H2 is 1629.7 kilojoules per kilogram. In the question, mechanical efficiency is given at 90%. The actual power input is the net power input, which is 7,000 watts or 7 kilowatts, times the efficiency 0.9. So the actual power input is 6.3 kilowatts. From the conservation law of energy, we know that the energy supplied to the compressor should be equal to the energy utilized by the compressor to raise the enthalpy. So the actual power input should be equal to the mass flow rate times the change in enthalpy for the compression. 6.3 kilowatts is equal to mass flow rate times H2 minus H1. Rearranging the equation, we can find the mass flow rate, and it is 0.033 kilograms per second. That is the answer for the first part of the question. To find part B, the equation for coefficient of performance of the refrigerator is equal to heat to evaporator divided by actual power input. The actual power input was already calculated in the previous steps as 6.3 kilowatt. To find the heat input to evaporator, it is mass flow rate times H1 minus H4. So using this, the coefficient of performance of refrigerator is 5.84. To find part C, the equation for coefficient of performance of heat pump is heat output of the condenser divided by the actual power input. The heat output from the content server is mass flow rate times H2 minus H3. So using the equation, we get coefficient of performance of heat pump 6.84.
Hope you have enjoyed and understood the calculation. If this was useful, please consider liking and subscribing. Also suggest engineering topics you'd like.